very quickly we resume, and Paul Alain Jacqmin will talk about classes of morphisms behaving like surjections.
Thank you. And first of all, I would like to thank warmly the organizers, because at least for me, it's the first conference on site since a very long time. So I'm really happy to be here to see all of you again. And I also would like to thank the scientific committee to let me the opportunity to talk today. So my talk will be about a very simple question, which vaguely could be stated as follows. Which classes of morphism in a category behave exactly like surjections do in the category set of set-sign functions? So I know it's very vague, so let's try to be a little bit more precise. So suppose you are given a finitely complete category and a class of morphism in it. Does it behave? Does it interact with finite limits exactly like surjection interact with finite limits in the category of sets? So, well, it's still very imprecise, but I will be more precise later on. But firstly, I will try to speak about counterexamples to that problem. And firstly, as we all know, in set, surjection can be categorically described as epimorphisms, so namely morphism with the right cancellation property. And these classes of morphism have some good properties, but it has a weak point, is that in the class of monoids, in the category of monoids, the inclusion of natural number into integers is an epimorphism. And so we have a proper mono, which is an epi. And again, in the category of rings, you have the inclusion of integers into rational numbers, which is also an epimorphism. And this property, so this phenomenon, does not appear with surjection in set, because we know if a surjection is a mono in set, it's an isomorphism. And so the first property we're going to require for class E is that there is no proper mono. So every mono in E is an iso. And therefore, the class of AP is not a good solution for a problem. So let's try something else. And we also know that the class of surjection in set can be described as regular epimorphisms, so namely coequalizers. And this class is good because in all algebraic categories, surjections are exactly the regular epimorphisms. And moreover, it satisfies the first property I mentioned. So if you have a mono which is a regular ep, it's an iso. However, it has bad properties that it's not closed under composition. For example, in the category cat of small categories, you can find two regular ep for which the composition is not a regular ep. And in set with surjection, this phenomenon does not occur, because if you compose two surjections, you get a surjection. And so as a second property, I'm going to require that the class E is closed on a composition, and therefore the class of regular EPs is not a solution to a problem. And so let's try a third class, because surjection can also be described as strong epimorphisms. So namely morphism E, for which each time you have a commutative square like that with a mono here, there exists a unique diagonal retaining the commutativity of the diagram. And it's equivalent, if you have finite limits, to the notion of extremal epimorphisms, namely morphisms which do not factorize through any proper mono. And again, this has really nice properties because surjections in any algebraic category are exactly the strong EPs, and the strong EPs satisfy the first two properties I described. So a mono, which is a strong EP, is an iso, and it's closed under composition. But again, in the category cat, they're not stable under pullbacks. So you can find a strong EP and a pullback of it, which is not a strong EP. And this phenomenon, if you have surjection, does not appear because we know that pullback of the surjection is a surjection. And this phenomenon is exactly what I said. It's an interaction between the class E and finite limits. And therefore, I'm going to ask that the class is stable on the pullbacks, and therefore the class of strong EP is not going to be a solution. So now let's make precise the problem. So I would like to find an embedding of C into, not into set because that's too strong, but into a pre-sheaf category. And the embedding will preserve and reflect finite limits. And moreover, it will interact well with the classes of APs I described. So namely, a morphism is in E, if and only if its image is a component-wise surjection. And if you have those properties, it implies that phi is faithful and conservative. So namely, it reflects equalities and isomorphisms. So that's the formulation of the problem. And immediately I will give you the solution. So this is the main theorem I would like to present. So suppose you have a small finitely complete category C, a class of morphism E in it, then the following two properties are equivalent. So the first one is exactly the embedding theorem I was stated. So there exists a small category G with a faithful conservative functor from C to the functor category from D to set, which satisfy the two properties I stated. So it reflects and preserves finite limits, and a morphism in C is in E if only if its image is a component-wise surjection. And this embedding theorem is equivalent to the following 5 conditions. So the first 3 are presented to you. So there is no proper mono in E, it's closed on a composition and stable on the pullbacks. And you need also to add the fact that E contains all identities and that it has a strong right cancellation property. So namely, if you have two composable morphisms whose composition is in E, then the second one should be in E as well. Okay, and you might, I call that the conservative embedding theorem because embedding is just conservative, it's not full. But there is also a full one. So if you want your embedding to be fully faithful, then you need to add one more property that any morphism in E is a regular AP. So now let's look at some examples of that. The first one, which is very basic, is a class of split epimorphisms. So a split AP records morphism with a section. And this class satisfies the condition for the full embedding theorem. And moreover, is the smallest one. So if you have another class E, which satisfies the condition in the embedding theorems, then it contains the split epimorphisms. And since it satisfies the condition for the full embedding theorem, you have a full embedding theorem. But this is well known for a very long time because if you take your NIDA functor, it will do the job. As a second example, so I've described the strong epimorphism, and I said they're not stable in the pullbacks, but we can stabilize them to get the class of stably strong AP. So what is a stably strong AP? It's a morphism E for which each of its pullback is a strong AP. And this class satisfies the condition for the conservative embedding theorem, but in general, not the full one. And we can prove that the big is such. So if you have any class E satisfying the condition for the conservative embedding theorem, then it's included in the class of stably strong APs. And I think the conservative embedding theorem for that is new, at least to me. As a third example, I have the stably regular epimorphisms. So it's almost the same definition. So morphism E for which each of its pullback is a regular AP. They're also known as descent morphisms. And this class satisfies the full embedding theorem. It's not quite easy because with that property, we stabilize them on the pullback. But why it's closed on a composition, it's not easy because regular APs are not closed on a composition. But this is due to Georgia Nidze, Manuela Sobral, and Walter Truman in 2004. And it's the biggest class satisfying the condition for the full embedding theorem, namely that all of them are included in the class of descent morphisms. And so since it satisfies the condition for the full embedding theorem, we have a full embedding theorem, but which is known. It has been proved by Barr in 1973, and he proved it using his own embedding theorem for regular categories. And as a last general example, we have the effective descent morphisms. I'm not going to recall what these are, but they satisfy the condition for the full embedding theorem. And this is not easy at all. So the fact that it contains identities and that each effective descent morphism is a regular AP That's easy. But the fact that it's stable on the pullbacks is due to Manuela Sobral and Walter Tolan in 1992. The fact that it's closed on the composition is due to Rutherford, Sobral, and Tolan in 1993. And the fact that it has a strong right cancellation property is due to Janizé, Sobral, and Tolan in 2004. And I've never seen the full embedding theorem corresponding to that class before. So that's all for the general examples. But let's see many examples in the category CAT of categories. So if we are given a natural number n, I'm going to define the class En of functors as follows. So each time we have, so there's a domain category, that's the codomain of the functor. Each time you have n composable morphisms in the codomain, I require that there are n composable morphisms in the domain, which are mapped by f to these given morphisms. So we can easily see that it gives a strictly descending chain of classes. And so what about E0? E0 is just the class of functors which are surjective on objects. And this one does not satisfy the condition in the embedding theorem because you have proper monos in it. E1 is the class of stably strong APs. This is due to Bernardczyk, Borzykowski, and Pawlowski in 1999. And it satisfies, so as we see in the condition for the conservative embedding theorem, but not for the full one. And then after that, after so E2, E3, and so on, they all satisfy the condition for the full embedding theorem. And E2 is a class of descent morphisms due to the same people. And E3 is the class of these effective descent morphisms. This is due to Janizé, Sobral, and Tolan. So it gives infinitely many examples in CAT. And we have even more of them, because if you take the intersectional of all these classes, it's another one, and it satisfies also the condition for the full embedding theorem. And it still strictly contains the class of split APs. Okay, so that's all for the examples. Now let me say a word about the proof of these embedding theorems. So one direction is very easy. If you have the embedding, then to say that the class satisfies the condition, it's easy because basically surjections in set satisfy those conditions. So that's the easy part. Now for the other direction, there is a proof that has been told to me by Zohar Janelidze, which basically goes as follows. So firstly, you embed C into the pre-sheaf category by Yonida. So that's well known. And then you have, so the class E of morphism in C induces a topology on C. And so you can describe the topos, so the sheaf category associated to that topology, and you have the sheafification from the pre-sheaf category to the sheaf category. And then, since the topos is a regular category, you can apply bar embedding theorem to go to another pre-sheaf category. And so bars embedding there, it's fully faithful and a regular functor. So that's very nice. And we know that a morphism in C belongs to the class E, if only if it is sent by AY, so the composition of the first two functors here, to an AP. So it's in E, if only if its image is an AP or equivalently a regular AP. And if the class E satisfies the condition for the full embedding theorem, you have that J, the topology, is subcanonical, and therefore AY is fully faithful. And so you get your fully faithful functor. And if E satisfies the condition for the conservative embedding theorem, then J, so then any pre-sheaf will be separated, a separated sheaf. And so AY will be conservative and faithful. So that's one possible proof, but there are downsides in this proof, because first of all, there is a size problem. So I know not a lot of people are careful about sizes, but let me still do it, because even if C is small, this category, this topos here is not. And so you cannot apply bars embedding theorem. Of course, you could change the universe by the axiom of universes. But then the embedding will be not in set to the D, but in a category of bigger sets. Okay, that could still do the job, but if you're really careful about sizes, that might be an issue. But another problem is that this embedding is totally not explicit. Why? Basically because Barr's embedding theorem depends on many transfinite inductions. And I know it has been quite a weak point of that proof. So yeah, that's very hard to get the description of the composite of these three functors. And a downside, because we don't have the description, it's going to be hard to generalize it. And what I'm thinking of is to replace here the class of morphisms, so of AP we have here, to a class of cospan, and to see when this class of cospan behave like the class of jointly surjective functions in set. Or if you prefer, you could just see which topology will be like the one of jointly surjective morphisms. So with this proof, it's going to be hard, but I have another proof I'm not going to present to you. But in the proof I have, there is no such issue, and it gives an explicit description of the embedding. And in this explicit description, there is absolutely no transfinite inductions. So that's something I like. It's still inspired by Barr's proof, but without any transfinite induction. And okay, it's a very long proof, but it's a very elementary proof. So just the first basic course in category theory is enough to understand it. And therefore, I hope to do the generalization I told you like previous slide. Thank you. And so I'm going to conclude by giving you an idea of the description of this embedding for the conservative embedding. So for the conservative embedding, we need first to construct the category D. I'm not going to say what it is, but just that the objects of D is the same as the objects of C. And then, so for the embedding, if you have an object C and an object D, so you should get a set phi of C of D. And this set is a quotient. So again, I'm not going to describe which quotient, but it's not very hard, but a bit long. But it's a quotient of the set of these finite diagrams. So these finite diagrams is just a tower of pullbacks, finite pullbacks, where the object here at the bottom is D, and where the top object is equipped with a map to C. And moreover, the morphisms here on the right, these are just products of morphism in E. So they're also in E, but each of these individual morphism in E are part of the structure. So it's an explicit description of the embedding. So since I don't have much time, I'm going to stop here. Thank you for your attention.
Are there questions? There is one question here.
Can you give an idea of why the full embedding theorem corresponds to requiring the morphisms to be regular epis?
Yes, because if you have so basically okay, perfect. So you have a morphism here in E. And so you have the image here, phi of E. And you want to prove, so you have the kernel pair here, and you take any morphism, and you should construct a morphism here. So you have the kernel pair here by the image. You have the image of this morphism, so this is F, so phi of F. But here, here it's a regular AP. So you get a morphism here, basically, and since it's full, you need a morphism here. Okay, I cheated just a little bit because to get the morphism here, you need the fact that this is a surjection, because otherwise, since these are natural transformations, so basically, if I apply to any object, sorry, D, yeah, D, you get a function here, but so that this collection of functions form a natural transformation, you need the fact that this is a surjection. But if you have that, it means.
Any more questions? George, we are going to open your mic. You can speak now. No, not yet.
May I ask a question?
Please.
So you have this nice theorem. Two things are equivalent. One is number of conditions on E. Another is embedding into pre-sheaf category. Can I trivially add the third one, replacing pre-sheaf category with any exact category, bar exact?
I guess so. Yeah, and then you need a regular function then. No. Yeah, I guess you're right. Yes. And then you want to send any morphism in E to a regular AP and vice versa.
Yes.
Yes. I'll have to check details, but I think you're right. Yes.
All right. Thank you.
Thank you for the comment.
More questions? If not, wait, maybe. No, then let's take Pierre-Alain again.